Hello, everyone. Thank you all for joining. Today, I'm going to present my research on long-term field performance of ready-mix recycled aggregate concrete. My name is Humera Ahmed. I am PhD student at UBCO, and my co-researchers are Mohammad and Dr. Shariala. This research highlights two full-scale field studies of recycled aggregate concrete in structural and non-structural applications, which are made with different replacements of recycled concrete aggregate. Long-term performance assessment of recycled aggregate concrete for 5 years in terms of in-place compressive strength using rebound hammer was assessed and presented here. Also, there was a strength correlation developed between in-place compressive strength and rebound hammer specifically for recycled aggregate concrete. The long-term strength of recycled aggregate concrete was comparable to conventional concrete. The flow of today's presentation is research motivation, introduction, methodology, results, conclusions, and recommendations. Research motivation. Canadian construction industry generates around 9 million tons of waste annually and recycled only 30% of it, which is very low compared to the other developed countries like Netherlands, which are recycling 98%, and Taiwan, which is 91%. Even though 52% by weight of this waste is composed of concrete, which has the potential to be recycled in the form of recycled concrete aggregate as a replacement of natural aggregate to produce new concrete. Just to elaborate the difference between the natural aggregate and recycled concrete aggregate. So you can see in this one slide the comparison between the two, natural aggregate, recycled concrete aggregate. The term recycled concrete aggregate for this presentation describes actually the recycled concrete coarse aggregate. So whenever in this term, the term RC is referred, it means that it's a recycled concrete coarse aggregate. For fine aggregate, we are using the natural strand in all the mixtures whose results are going to be compared in the upcoming slides. So continuing with my research motivation, substitution of natural aggregate, the substitution of natural aggregate by RC offers a promising solution for the problems of natural resource preservation, land reclamation, and reduction in the number of loads headed to landfill, thus showing that RCA is sustainable, at least for these three reasons. Keeping in this view, various countries in the world have standardized the incorporation of RCA in the production of structural and non-structural concrete. For structural concrete, the maximum percentage of RCA, that is 100%, is permitted by RILEM and Danish standard, followed by German standard 90%, Italian standard 30%, and so on. Surprisingly, percentage for non-structural concrete, that is also ranging from 100 to 20%, and Canada lies for non-structural concrete 100% use. A growing body of literature in the lab setting has already recognized the importance of utilizing RC in the production of new concrete. In thus, utilization of RC in the large-scale industrial production of new concrete is not widely accepted by international standards due to its high porosity, a disparity of source concrete, and a lack of territorial studies. Keeping all above in view, this research was planned in 2013 to provide an insight to the applicability of recycled aggregate concrete to the southern interior of British Columbia, Canada. This study was a collaboration between ALAM's research group, City of Kelowna, and OK Builders. Two full-scale field studies of the construction of foundation system, base wall of a 2-story wooden house, and a municipal sidewalk. The results of this research are based on laboratory investigations and assessment of the in-place long-term performance of recycled aggregate concrete made with different replacement levels of RCA. From this, in this slide, you can see the in-process construction activities on these projects. The first slide, that is to the left top, marked as A, is showing you the in-process activities of the casting of the foundation system of the residential building. This photo B is showing the in-process construction activities for casting of a sidewalk. In addition to these two field studies that we have conducted, that is the foundation system and the sidewalk, there was a concrete block was also poured at the time for the laboratory investigations and for the development of strength concrete. You can see this concrete block pouring going on in this one photo. on the slide. Now this slide explains the methodology that which type of concrete we use for concrete block, foundation system, and sidewalk, which are the target strengths, which are the exposure categories, and which is the RC replacement. Just to be quick overview to explain the nomenclature that we are going to use in the results and in this presentation, that is that when you see foundation system, it says that the foundation system concrete is represented by R30-25, where 30 stands for percentage replacement of natural aggregate with RCA, and 25 stands for the target strength to be achieved at 28 days. Similarly, for the sidewalk, there was a couple of nomenclatures that you can see under the sidewalk bar that says that R032, R30-32, 50, 70, 100-32. And over here, the subscript shows a percentage replacement of RCA, whereas the dash after the numbers is showing the target strength. Continuing with the methodology, all the mixtures are batched and mixed in the OK Builder facility and transported by their trucks to follow the commercial practices. In addition to that, when we were pouring the sidewalk, the total length of sidewalk was 200 meters, which was subdivided into 5 parts in such a way that every 40 meters was cast with a different RCA replacement level to provide a comparison under the same exposure conditions. And the percentage replacement at every 40-meter section was marked on the sidewalk. You can see in this photo, so that when we go later for the long-term study and getting our results for the rebound hammer, we will able to know clearly that, okay, which sections starts from this end and where it ends. So that's why the percentage replacement was marked on the sidewalk at the spot. The raw material used in the production of RC was collected from the landfill to represent the real world situation of commercial construction. So the mixtures was used, the one that was always used for ready mix concrete, for conventional concrete, and also we collect all the RC from the landfill just to give as much realistic approach as possible. This slide shows you the gradation characteristics of the coarse and natural aggregate. The gradation curve was obtained by using the sieve analysis as per CSA, and you can see that the aggregates that are used, they totally fit within the CSA upper and lower limit for both coarse aggregate, natural coarse aggregate, RCA, and the fine aggregates. You can see also the physical properties of the aggregates on this one slide. To produce RCA for this study, firstly, demolished concrete was visually inspected. And any large impurities like steel, wood, they were removed manually. Then this demolished concrete was spread into the jaw crusher for primary crushing and screening into different sizes from 5 to 20 millimeter. The particles were stockpiled in different sizes after washing to remove recycling, dirt, and lightweight contaminations. So this is the way how we get our RC to be used in this one research. Now it comes towards the concrete mix design. You can see over here the concrete mixture constituent per cubic meter. Just to give you a quick refresher, that R2025 was designed for category C2 as per CSA, R30-25 was designed for category F2, exposure category F2, and R032 is designed for the exposure category, again, C2. Now coming over the testing scheme, that how we test our concrete and how we develop the relations. First of all, for the concrete block, we test cylinders, which are casted with the concrete block for the compressive strength assessment at 7, 14, 28, 56, and 90 days. Then we drill the cores, but the cores were drilled at 14, 28, 56, and 90 days. And rebound hammer test was done in the same way that when we are going to drill the core, we are taking the readings of rebound hammer at that time. For the foundation system, we work with the cylinder, we tested the cylinders that were casted with the foundation system, and for the sidewalk, the procedure of testing the specimen is same, but the time of taking the data and testing the specimens is different. It shows in this one table. Now, this slide represents or summarize a quick reference for all the cores that will be used for our testing and development of core, drilling the samples, getting the samples, and also for development of the strength correlations. Over here, you can see that the temperature, the minimum temperature per month during these 5 years to which foundation system and sidewalk were exposed to, so to get an idea of that how much severe climate that these concretes has faced, and when the results we are going to report are relying on these extreme conditions of the weather. Now talking about the results, over here you can see that the results of compressive strength of concrete cylinders and cores according to the scheme provided earlier shown in this one slide. As it can be seen from the graph, our 2025 successfully achieved its target strength of 25 megapascal at the age of 28 days. Also with time, strength increased in a similar fashion as generally associated with the conventional concrete. In addition to that, average concrete compressive strength of the drill cores also satisfy the criteria for structurally adequate concrete, which is 0.85 FC prime, and compressive strength are 0-32 and are 132 of sidewalk mixers at early age at 7 days that have achieved, and then in 28 days, you can see that all mixtures except 2 have reached their target strength of 32 megapascals. So the primary reason between the variation in the compressive strength of sidewalk concrete mixes seems like to be that percentage difference in the percentage replacement. Now coming towards a strength correlation. So based on the results that we have shown in the previous slide of the compressive strength and rebound number, 2 strength correlations are established and following the ACI method, one between the natural logarithm of compressive strength of cylinders and rebound numbers, and other between natural logarithm of compressive strength of compressive drill cores and rebound number. And in addition to that, you can see over here green line that is basically the rebound hammer reference curve, that is the lowest 10 percentile curve. It is presented over here just for the comparison purposes. You can see that the estimates of a cycle aggregate compressive strength using their hammer reference curve are very conservative to those obtained from the cylinders and core strength correlations, because the strength correlations provided by the manufacturer are mostly generalized. They are based on the standard of testing, based on testing of standard concrete, and are not suitable for concrete with a non-conventional composition like recycled aggregate concrete. For rebound hammer testing, stiffness of aggregate plays a vital role in defining the stiffness of concrete on which the rebound number is based. And RC has lower stiffness than NCA, natural aggregate, due to adherent mortar. Thus, developed cylinders and core strength relations for recycled aggregate concrete is likely to be preferred more for estimating compressive strength than generalized reference curves that are provided with the hammers, with the rebound hammers by the manufacturer, even though they are based on a larger data set, but again, they are not specific for the particular type of aggregate we are using in our concrete, that is cycle concrete aggregate. For this research, limitations are on the slides. That this research, the correlations developed for concrete, which has 20% RC replacement with 25 megapascal target strength. Rebound, it is validated for rebound numbers starting from the range of 45 to 60, and 20% criteria is considered as a comparison between the results. This slide shows you the results we obtain in 5 years, and you can see the comparison between the cylinder the compressive strength, in place compressive strength obtained by using the cylinder correlation, in place compressive strength obtained by the core correlation, hammer, and the design target strength. You can see that overall values from developed correlations are within a 20% of hammer correlation for all the 3 locations and the 2 test durations, that is 3 years and 5 years.
3 minutes left.
Thank you, Ahmed. Like the previous slide, this slide shows estimated 10 percentile in-place compressive strength of sidewalk mixtures. Estimates of in-place compressive strength from core correlation and hammer reference curves are very close for R032 and R30-32. They are similar to the foundation concrete, but with increased percentage substitution of RCA. Core correlations results are the lowest with higher standard deviation. In addition to that, I want to just present you a couple of slides that's showing us the serviceability of the sidewalk. So over here, you can see the photo of the sidewalk captured after 5 years in service. This sidewalk was heavily used by the pedestrian traffic. This was in a residential spot, so there was parkades for the many houses, so used by the cars, and as you can see, there's heavy traffic used sidewalk. Even it has a bus stop, and you can see that there's no cracking, wear and tear, or maintenance required even after exposure to the freeze and thaw conditions. And temperatures as low as -24.8 degrees centigrade. Generally, concrete exposed to freeze and thaw developed arbitrary surface cracks with scaling and weakening of joints because of D-cracks caused by the non-durable aggregates. So for comparison, you can see in the next slide, the sidewalk casted at the time, where that photo taken is the time of casting. And over here, you can see the photo after 5 years, and you can see literally no difference in the serviceability. Now coming towards the conclusions, so quickly wrapping up the conclusions. After this research, we can conclude that RCA has significant potential of using a substitution of an HO aggregate for targets compressive strength of 25-32 megapascals. Compressive strength of our cycle aggregate concrete increases in a similar fashion as we expect from the conventional concrete. The one benefit is that cycle aggregate shows a higher rate of compressive strength development as compared to conventional concrete after 28 to 128 days of curing. This fact is more pronounced with a 30% RCA substitution. The long-term performance is giving you all the good results for different percentage replacements. We validate the result using the cylinder correlation and core correlations, and Humera reference curves are developed for both cylinder and core strength relations. Overall, the long-term in-place performance for cyclic concrete is adequately comparable to conventional concrete in terms of serviceability as well. So no issue has been reported since its placement at site, that is 5 years. Now, recommendations. You can see the recommendations for this research. We want to proceed further with the research with the core testing as well. But by providing an insight into the sustainable application of RCA in the production of new concrete, the result of this study can serve as a basis for updating the current standards in Canada and permitting the use of cycle aggregate concrete towards the structural applications. These are the references, and at the end, I would like to thank our academic acknowledgement to OK Builder, City of Kelowna, Hugh, whose house was built by the cycle aggregate concrete foundation system, and ANSER for providing and funding this research. Thank you very much. Any questions?
Thank you very much, Humera. So very good presentation. So we have, again, we have the Q&A button or tab on Zoom. So please, if you have any questions, please just go ahead and post your question. I think we still have about 2 minutes. I think we have one question. It says, can RAC be used for reinforced concrete walls and beams?
So the particular research, that is this research under the lab settings, in the literature, published literature, it says yes, they can be used. But as far as the research on the large scale field applications and getting the data on site, our research group is working towards that. So we are trying to explore different situations where can we apply the cycle aggregate concrete in the reinforced concrete walls and beams. As far as comes towards the foundation walls and the basement walls, I can say yes, the results of my presentation shows that. But as far as the results in field results of the reinforced concrete walls and beams, they are not here up till now. But as far as lab settings is, yes, we can use it. Thank you, Greg, for your question. Actually, the purpose of this research mainly is to see that what is actually happening at site, or you can say in full-scale field studies. I agree that there is a concern about dry shrinkage because of you can say high porosity of cycle aggregate concrete, and as soon as it comes cycle concrete aggregate, and as soon as it comes in the form of a concrete mix, it starts absorbing the water and causing the concrete to shrink. But our scope of work doesn't go towards the detailed lab settings. We are just focusing to see the actual applications of concrete in the field, and that was there. And you can see that if we talk about serviceability, we have no issue, or you can say no problem with the users of the residential building who are using that house, reporting about any causes or aftershocks of serviceability towards a drying shrinkage. So actually, first of all, our scope is not there, and then I will receive the serviceability.
Did you consider the drying shrinkage? I have a question here actually. So
I'm trying to answer that. We don't consider a dry shrinkage because the scope of study is totally different. We want to apply the concrete in the field applications. But as far as we can say that a dry shrinkage towards serviceability, there was no issue regarding that in terms of serviceability.
Okay, one more question here says, does the compressive strength of the concrete increases or decreases compared to using natural aggregates?
For recycled aggregate concrete, the basic problem that we say that we usually find this reported in the literature, that the compressive strength of recycled aggregate concrete is lower than the conventional or natural aggregate concrete. So for now, the purpose is just to make sure that the recycled aggregate concrete able to reach the same strength as of the conventional concrete. So currently we are trying to bring that standard up, that okay, it can't be lower, it can give you the same performance as a conventional concrete. So for our research with the different replacement ratios, some concrete lag to achieve their target strength at 28 days, but when you test them at 120 days, they reach there with a higher gain in the compressive strength. And obviously after 5 years, with the help of a rebound hammer, we inject the results, they are same like a conventional concrete. So yes, I can say that they can reach to the conventional concrete, but sometimes there's an increase and sometimes there's a decrease, but it can reach to the conventional concrete strength.
Okay, one final question here. How old concrete is sampled for use as RCA? Is there a criteria, for instance, the size of aggregate, the age, or the environmental conditions? So the old concrete was exposed to? I'm just reading the question. So yeah, go ahead, sir.
Thank you so much for this question. So the concrete that we were using was actually collected it from the landfill. So it's just have a disparity of source. Because when we have the RCA, we cannot take RCA from the laboratory waste and use it in a field study. When we go into a field study, obviously we need a huge amount of RCA. And when we go for the huge amount of RCA, we always have to look towards the landfills where RCA was municipally allowed to be dumped. And when we take the RCA from there, it can have any age of RCA that is dumped over there. It can have any source of RCA. Maybe it's a structural concrete over there, maybe it's non-structural concrete over there, maybe having a strength of 32 megapascal, maybe a 50 megapascal. So it's a total variation, just random concrete waste, which was crushed into the size that is required from like 20 millimeter to 5 millimeter to be satisfied as coarse aggregate requirements. And we just crush it and take it report in the application, so we can give a real world solution. It's not a laboratory investigation, it's a real world solution focused thing. So it was exposed, it was of any age, of any basic strength.